Hello dear students, I am Pratima. I welcome you all to this video. I hope you are ready for class 10 syllabus. So today we are starting real numbers, Euclid's division lemma, Euclid's division algorithm. What is the difference? And we will solve exercise 1.1 as well as we will solve a famous egg counting problem given in examples you must have seen in the textbook. So Euclid division lemma is just a theorem stated by Euclid, the great mathematician. Given that the positive integers a and b for two integers a and b, there exist unique integers q and r satisfying A is equal to B times of Q plus R, where R value is from 0 to less than B. Now it is written in AB, that's why it is slightly confusing or we don't want to understand. But if I'll write in the using integers, you'll see that it is not difficult, it is very simple. It is just like your division algorithm you have read in lower classes. We are applying that division algorithm I am writing. So what do we write? We write dividend is equal to divisor multiplication your quotient plus remainder. So dividend is your A, divisor is equal to B into quotient Q plus R. And you know that the remainder is always less than your quotient divisor. Now let us take the example. Suppose A is equal to 13, B is equal to your 6. Then we can write 13 is equal to 6 multiplies 2 plus your 1. 13 divided 6. 6 2 times 12. 1 is remainder. So 2 is quotient which is multiplied with 6. R is remainder plus return. Let us take another example. 25 and here it is your B is 4. So I can write 25 division 4. You know 4 6 times your 24 and 1 is remainder. So this is your quotient Q, this is your R, and it is saying it is always unique. It cannot be same for two numbers. So 25 is equal to 4 multiply 6 plus your 1. So 6 is Q quotient, 1 is your remainder. So can you think of any other example? Suppose 32 and B is equal to 5. So how to write? 32 is equal to 5 6 times plus 2. So Q is your 6, R is equal to your 2. Next, what is the algorithm? Algorithm is your procedures or it is the steps where we use this lemma to find the HCF of two or more numbers. So what is Euclid's division algorithm? It is the procedure to use the lemma or theorem to find HCF. So they are not same. One is procedure to apply the theorem. So this algorithm is nothing but your procedure and it uses the lemma to find HCF of two or more numbers. Now let us see what is the steps. Now to obtain the HCF of two positive numbers, say C and D, where C is greater than D. I am taking two numbers C and D, C is greater than D. Then follow the steps below. First step is apply Euclid's division lemma to C and D. What is the application? We'll write C and D in this form. What is it? C is equal to D into Q plus R, where R is greater than equal to 0 and less than equal to D. If the remainder is 0, then D is HCF of C and D. Now let us take one example so that you will understand better. I am taking two numbers 15 and your 3. So I can imagine C is equal to your, this is your small c and this is your small d, because 15 is greater than 3. I will find the HCF of these two. What I'll do? I'll divide 15 division 3. I'm getting 3 5s are 15 and remainder is 0. Whenever I'll get remainder 0, D is your HCF. So HCF of 15 and 3 is 3. So this is explaining that what? Now if C can written as dq plus r, I am writing 15 is equal to 3 into plus 5 plus 0. Whenever this remainder is 0, then the D is your HCF. So 15 and 3, HCF is equal to 3. Now what will happen if R is not equal to 0? If R is not equal to 0, then we'll use the division lemma to D and R. That means to the divisor as well as your remainder. Let us take one example. For example, I'll taking your 28 and your, not 28, I'm taking 20 and 38 and your, it is also divisible. Let me think of some other number. This is not the number. I'm taking 48 and your 36. I'm finding the LCM of these two. So C is equal to 48, D is equal to 36. I'm taking one example where I'm not getting remainder 0. So 48, if I'll division your 36, then 36, 1 is 36. So how much is left? 12 is remainder is not equal to 0. When remainder is not equal to 0, what I'll do? I'll apply the division algorithm for this 12 and 36. That means this is D, this is your R. That means again I will divide 36 with 12. D will be divided by 12. Then 12 3 times is 36. Till I get the remainder 0, it will be continuous. So how to write this one? I'm writing 48 is equal to 36 multiplies 1 plus 12. So this is my D, this is small c, this is small d, this is your R. Then I'll apply your dr, this lemma. What is it? 36 is equal to 12 multiplies 3 plus 0. So 0 is the remainder. So now R will be, R is your HCF. So it will go on. If again I'll not get remainder, I'll go for next step. So the continue this process till you get remainder is 0, and when we are getting remainder is 0, or that R is your HCF. So I'll take an example so you will understand better. I'm taking the divisor at these stages will be the required HCF at each step. Whenever you are getting remainder is 0, at that step divisor is equal to HCF. So I'm taking exercise questions. Question number 1, use Euclid's division algorithm to find the HCF of first is 135 and 225, 196 and 38220, 867 and 255. So we'll go one by one. First I'm solving part 1. 135 and 225. So which one is bigger? 225 is bigger. So I'll divide 225 with your 135. How much I'll get? Certainly I'll get 135, 0, this will be 9. I'll write now the step 225 is equal to 135 into 1 plus 90. Here the remainder is not equal to 0. Then I'll go for second step. So 135 I'll divide with 95. So 190 multiplies 190, I am getting 45. So this step I'll write here because this you are doing the division, but this is the algorithm you have to show in the test. So here I'll write 135 is equal to 90. That means D will come to the place of C and your remainder will come to the place of D. 90 into 1 plus 45. Still remainder is not equal to 0. Then again your 90 will be in place of your C and 45 will place of D. So 45 2 times your 90. So I am getting now remainder is 0. So I'll write this step also. So 90 will come here in place of C. 90 is equal to 45 multiplies 2 plus 0. Whenever this remainder is 0, stop here. Then declare this HCF is equal to 45. This remainder at this stage where you are getting the remainder is 0, divisor is equal to HCF. HCF is the divisor, that is your 45. So I hope you have followed. You can note down the procedure. Now coming to second part. Second part is your 196 38200. 38220 is the bigger one. So I'll divide 38220. Division your 196. Go on dividing 196. Subtract. You will get 6. 7, 9. 7 minus 9, 8. And here 1, 2. Then I'll go for 9. Here I'll get 9, 6 times 54 carries 1, 6, 1, 7, 6, 4. Then I'll get 9, 8, again 0. Very interestingly, I'm getting the remainder 0 at first step only. So I'll write 38220 is equal to 196 multiplies 195 plus 0. So C is equal to D multiplies Q plus 0. Then D is the HCF. So 196 is HCF of 196 and your 38220. Next coming to third part. Third part is 867 and 255. So 867 is greater. So I'll divide 867 by 255. This is your rough work. 1, you will divide, how much you will get? You will get first, it's not 3, directly you will get 3. 25, 3 times 75. So you will get 765. If you subtract, you are getting 102. So write the step immediately. 867 is equal to 255 multiplies 3 plus 102. 1 into 2 is the remainder, it's not 0. So again I'll divide 255 with your 102. So it will be how much? It will be 2204, then it will be 51. Write the step immediately. So it will, you will write 255. So you can see the pattern. The 255 is coming here and 102 is coming here. So 102 multiplies 2 plus your 51. Next is remainder is not 0. So I'll write 101 here. 202 LCM with this remainder is 0. So next write the step. 102 will be here. 102 is equal to 51 will be here. 51 multiplies 2 plus 0. So now stop. So when stop, 51 is HCF of 867 and 255. Next question is use Euclid's division algorithm to find the HCF of, oh, we have already done it. We have already done it. Next is question number 2. So that any positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, where q is some integer, these three will be the odd. So about this odd integer, and even integer, Euclids gave the idea if any integer is multiple of 2, then it is a even number. If any number is twice m plus 1 for any integer m is an integer. If m is integer, then 2 into m is equal to even. You know 2 multiple is even, and 2m even plus 1, it is always odd. So now the numbers are 6q plus 1, 6q plus 3, 6q plus 5. So if we'll write 6q plus 1, so 6q is equal to how much? It will be 2 into 3q plus 1. So 2 into 3q your even, then your plus 1 is equal to your even number plus 1, it is a odd number. Okay. Similarly, 6q plus 3 is equal to, we can write 6q plus 2 plus 1. And this is a even number. Why? I can take 2 common. So this will be 3q plus 1 plus 1. This is even plus 1. That will be again odd number. Now 6q plus 5. So this I'll write 6q plus 4 plus 1. I'll take 2 common from this. So this will be 3q plus 2 plus 1. And any multiple of 2 is even number plus 1. So this will be a odd number. So 6q plus 1, 6q plus 3, 6q plus 5 are odd integers when q is any integer. So any multiple of 2 is a even. Next number, successor of it is a odd number. This concept we are applying, and we are applying 6q can be written as 2 into 3q. So it is even. So even next number, what is the next to your even? That will be odd. In this way, we have to write 6q plus 3. So I splitted 3 as 2 plus 1. I took 6q plus 2 together, and I took 2 common, so 3q plus 1 is left. So whole this one is even plus 1, that will be odd number. Similarly, for 5, I took 4 and 1. Then 6q plus 4, I grouped them. I take 2 common. I am showing that they are multiple of 2. For any integer cube, this twice of this is equal to even. Even plus 1, that will be odd number. Or this question can be written in another way. What is it? You can write that using these numbers, whatever, using lemma, using Euclid's division lemma, any integer can be written as 6q plus 0, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, up to how much? 6q plus 5, up to this, because I am taking your b as 6. So A is equal to BQ plus R. The value of R is 0 to B. So B is here 6. So R value will be less than 6. It will be up to 5. R is equal to 0, R is equal to 1, R is equal to 2, 3, 4, 5. So the integer is A. I'm not writing it. Maybe 6q, maybe 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. So 6 cube is equal to 2 into 3 cube. So this is your even number. So if 6q is even, 6q plus 1 is odd. If 6q plus 1 is odd, next number will be even. Similarly, 6q plus 3 will be odd. 6q plus 4 is even. 6q plus 5 is odd. So 6q plus 1, 6q plus 3, 6q plus 5 are always odd integers when q is an integer. Of course, they are positive integers. Question number 3. An army contingent of 616 members is to be marched behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? That means 616 members are there and 32 members in a one column. So that means the number of columns are divisible by 616 as well as 32. So what is it? It is HCF of 616 and 32. How to find it? You can find in any method. You can use the prime factorization method also. No need of getting this uh, division method. It is not mentioned here. So 616 and 32. You can also use the methods. So 616 is and 32. So I'm going for 4 first. 4 1 4 2 5 and 4 4 just 16. Here 4 8. Next is I'll go for 2. So 2 sevens are 14. 2 sevens are 14. 2 4. So what is it? It will be 4 SF is equal to 4 into 2, that will be 8. So the maximum number of columns is 8. Next is question of 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Here it is given to you, the hints is also given. Let the x into positive integer and let us write it is 3q, 3q plus 1, then 3q plus 2 form, and now square each of the number and show that they can be in form of 3m, 3m plus 1. So we are using the lemma in this way. A is equal to bq plus r. Here I am taking as b is equal to 3. So when b is equal to 3, r is equal to 0 and 1 and 2 because it will be less than 3. So the numbers will be what? 3q when r is 0, 3q when r is 1, 3q plus 1, 3q plus 2. So the numbers are 3q, 3q plus 1, 3q plus 2. So let a is equal to b plus 1, let the numbers are, let the integers are. Now we'll prove the square of this is either 3 into m, 3 multiple, or 3m plus 1. It is not, m is not a number, any multiple of 3. It can be 15, it can be 24, it can be 48, so on. Similarly, it can be, if m is 15, it can be 15 plus 1, 16, so on. So first I am coming to 3 times of q. I'll make a square. So 3q square is equal to 9q square. So I'll make into, now just observe whether it can be made into 3m or it will be 3m plus 1. Certainly it will be multiple of 3. So I'll show, to show the multiple of 3, I'll take 3 outside. So how much will be left? 3 3s are 9, so 3 will be left and the whole q square will be left. So in place of 3q square, I can write this is an integer, 3m. So it is in this form now. Now coming to second one, 3q plus 1 square. Here I'll apply a plus b whole square. A square, 3q square plus 2ab, 2 into 3q into 1 plus b square, that will be 1 square. So this will be 9q square plus 6q plus 1. Now observe, can it be in this form? No, it will be plus 1 is extra is there. So what we'll do, we'll group them, this one, these two. And from this group, I'll take a 3 common to make into a 3 multiple. So 3 common, so what will be left? It will be 3 is left, 3 3 is 9. Q square will be left. Coming to second term, I have taken 3, so 2 will be left. Q will be left. Plus 1. So it can be imagined that 3q plus 1 whole square is equal to 3 into any integer. Instead of this, I can write one integer which is represented by m plus 1. Now coming to third one. Third one, I hope you can pause the video, you can try yourself. So this will be in the same way. First is a square. So 9q square plus 2 into 3 cube into 2 plus 2 square, it will be 4. Now I am getting 9q square plus this will gives you 12q and plus 4. Plus 4 is not there. Plus 1 is there. And 3 multiple is there. So 4 I'll split to 3 and 1. This is only the trick you have to do here. You have to remember. Then I'll group this and I'll take a 3 common from this. So if I'll take 3 common, I am getting 3q square. For second, I'll get 4q. For third, I'll get 1 only. So 3 into 3q square, 9q square. 3 into 4, 12q. 3 into 1, 3 plus 1. Again, instead of 3q square, 4q plus 1, I'll write a m. So 3 into multiple, which is an integer, plus 1. So proved. Coming to fifth question. Use Euclid's division lemma to show that the cube of any positive integer, we finish square, now it is cube, 9 times of integer, 9 integer plus 1, 9 integer plus m for any integer m. So where to start? We'll start from the same concept. First you will write a is equal to b cube plus r, where r is in between 0 to b. And here I'm not equal to, only less than. So here I'm taking b as 3. So the numbers will be, the integers are 3q plus 0, 3q plus 1, 3q plus 2. Can it be more than that? No, because b is 3. It cannot be equal to 3. Now I'll show that they are cubes. So for that cube, you need the formula of a plus b whole cube. I hope you have remembered. This is a cube plus 3a square b plus 3ab square plus b cube. So first is 3 cube. It is simple. It will be 27q cube. So I'll prove that it will be in form of 9m, 9 multiple. So take 9 common. How much will be left? 3q cube is left. So it will be 9m. Proved first one. Next coming to 3q plus 1 whole cube. First I'll put the formula very correctly. It will be 27q cube plus 3 into 3, 9 into 27q square plus 9q plus 1. Then what's I'll root? This will be 9m plus 1 form. 9m plus 1 form. So I'll group these 3 and I'll take 9 common. So I'll write 3q cube plus 3q square plus q only, 9 I've taken common, plus 1. So this can be written as 9m plus 1. Second is proved. Now coming to third one. We proved this 9m, this is 9m plus 1. Now coming to 3q plus 2. So 3q plus 2 cube. So it will be 27q cube. Same formula I'm applying. A plus b whole cube. A cube plus 3 a square b. 9 into 3. 27 into 2. 54q square. Plus 4 into 3. 12 into 2 into 3. 3 into 4. 12 into 3. 36. 36 cube plus 2 cube is equal to 8. So here I'll make into 9m plus 8. So 8 I'll make free. These 3 I'll take common. What I'll take common? I'll take common because I have to say show it 9m plus 8. So if 9 common, I'll get 3q cube plus 6q square plus 4q plus 8. So this will be 9m plus 8. So cube of any integer are in form of 9m, 9m plus 1, 9m plus 8. Then I'm coming to example Euclid's division lemma, another application which is very interesting riddles. Many people ask others. A trader was moving along a road selling eggs, and idler who didn't have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled the basket with the eggs and dashed into the floor, the eggs broken. The trader requested the panchayat to ask the idler to pay for the broken eggs. The panchayat asked the trader how many eggs were broken. He gave the following response. If counted in pairs, one will remain. If counted in the threes, two will remain. If counted in fours, three will remain. If counted in fives, four will remain. If counted in six, five will remain. If counted in seven, nothing will remain. My basket cannot accommodate more than 150 eggs. So how many eggs were there? If counted in pairs, that means the number, if it is divisible by 2, then 1 will be remaining.